All right, let's go ahead and take some additional vector notes based on what we saw in the last two videos. The first thing we're going to talk about is a new way to measure direction using the cardinal directions. So we have been looking at measuring a direction using an angle and basing that on calling this the x direction and this the y direction, and then saying, okay, right here is the angle relative to the x direction. And we're still going to basically do that, but we're going to change that up a little bit, okay? So I'm going to change this. I'm just going to get rid of all this. And the cardinal directions are what you are used to from your looking at a map. Not that people these days looks at maps, but you know, maybe you do. And this direction is north. That makes this south. That makes this east. And that makes this west. Okay, so if I had a vector A, let's say, that laid right along the axis there. And then let's get another vector, and let's call this vector B. And I'm going to go ahead and call that vector B. And I'm going to know that this angle right here, say, is 65 degrees. Okay. So when I look at A, I'm not going to say that A is necessarily 0 degrees. When I'm given my direction for A, and we're not going to worry about the magnitude right now, I'm just going to say that the direction for A is due east. Okay. When I'm looking at B, B is a little tougher because B isn't due east, right? And it's not due north straight up, and it's not due east, so it's northeast. But northeast is a big range, right? It's pretty much anywhere in here would be northeast. So we have to be more specific. So we're going to go ahead and say that B is at an angle of 65 degrees, and I'm going to measure that angle from the east. So it's 65 degrees going this way away from right. I'm always going to start at my east, north, west, or south line. So since I'm measuring the angle always from one of these, and I've got this 65 degrees, I'm going to say that that's 65 degrees, and I have to go north of east to get that angle. So I'm going to say that this is 65 degrees north of east. Okay. Now, obviously, with an angle like that, and we're always going to have angles between 0 and 90 degrees using this method. Obviously, if that angle is 65 degrees, this angle right here is going to be 25 degrees. So I could say for B, instead of saying it's 65 degrees north of east, I would be just as accurate if I were to say, actually, I like to say it's 25 degrees, but now, since I've measured that angle from the north, right, and I have to go from the north and I have to go east to get to the vector, I'm going to say that that is 25 degrees and it's east of north. So that's how we're going to measure vectors, especially when we are talking about relative velocity, something like a boat or a plane, okay? The next thing we have to understand when we're talking about boats or planes is this idea of upstream and downstream. So we're going to define downstream. And downstream is if we're talking about a boat, we might be talking about a plane. Sometimes it's basically the same idea. Or downwind simply means that the boat or the plane or whatever is traveling with the current. Right? It's in the same direction as the current. Okay. If we say that the boat is going upstream or the plane is going upwind, then we know that the object is traveling against the current, okay, in the opposite direction. Okay, so it's the opposite direction of the current. Okay, so it's really important to understand those because we're going to use that terminology in a lot of our problems. So here's the process that I use, and these are the steps that I take when I'm going to go ahead and I'm going to add two vectors in order to find the relative velocity. Okay, so we'll go ahead and call this relative velocity steps. Okay, the first thing I always do is I always draw the vectors. Okay, I always draw them because I really like to get an idea of what's happening, a visual idea of what's happening. So I'm always going to draw the vectors that I'm given. Okay, start with that. It's going to be a much easier problem to do if you go ahead and take that step. Can you do it without drawing the vectors? Absolutely you can. But when you start making mistakes, you realize that that was a bad idea, okay? So the second step then, after I do that, is I'm going to want to calculate the components of each of the vectors, okay? We're going to need that because I can't add vectors without knowing the components, okay? Then I'm going to go ahead and I'm going to do that addition. I'm going to figure out what the resultant is in component form. Okay, so that's our next step. Oh. And then, last but not least, I'm going to go ahead and I'm going to recombine those components into a magnitude and a direction format. Okay, so I'm just going to convert those to a magnitude and direction format. Okay, so a couple things to keep in mind, and let's talk about a boat first. Okay, we want to find the resultant or the relative velocity. Okay, and we're going to do that because I know that that's going to be the velocity of the boat plus the velocity of the current or the water or the stream, whatever we want to call it there. If I'm dealing with a plane, I'm going to have something different. I'm going to have my resultant velocity is equal to the velocity of the plane plus the velocity of the air or the wind, whatever we want to call that. And of course, we have to add those as vectors. Okay, so let's try an example. Okay, so in our first example, we know that a boat can travel at 20 miles per hour, right? That's its max engine speed when there's no current, okay? What if we want to know what's the speed of the boat and the max speed of the boat when it's going at 20 miles per hour, when it's going against a 5-mile-per-hour current. Okay. Now, this is obviously a pretty simple problem, but let's go ahead and draw these, and we can pick some directions here because we're not given many directions, okay? So if I draw the velocity of the boat, then I'm going to say, well, okay, it's going due east, right? I can say that the velocity of the boat is 20 miles per hour. And then if it's going against a 5-mile-per-hour current, well, then I know, and I want to connect these tip to tail, and I can't do it directly on top of each other, so I'm just going to kind of estimate right here. And I'm going to say, well, the velocity of the water is 5 miles per hour the other way. Well, then I can go ahead and I can draw the resultant, right, just like I always have, starting at the tail of the velocity of the boat, ending at the tip of the velocity of the water. Boom. There is my resultant velocity, which you probably already knew, right? And that's already broken down into components. So I know that the resultant velocity is going to be 15 miles per hour. And in this case, we could say it's east. I drew it east, right? We didn't say that in the problem, but we could figure that out, okay? All right, let's take another example, and let's use the same boat and the same current, okay? And let's say instead now, we want to know the velocity of the boat relative to the shore when the boat travels across the current. Okay, what's the resultant velocity or the relative velocity of the boat? Okay, so that's what we're trying to find, the relative velocity of the boat. Okay, so we're going to use the same ideas. Okay, I'm going to go ahead and I'm going to draw the velocity of the boat. I'm going to still assume that the current is going going west like we had it before. So here's the velocity of the water. And now I know that the velocity of the boat is 20 miles per hour. Okay, so I'm going to draw that right here. And let's see, here's the velocity of the boat. I know that this is 5 miles per hour, and I know that this is 20 miles per hour. I want to know the resultant velocity, so I want to know this velocity right here. Well, I can break these down into components, but they're really already in components, right? If I was going to go ahead and write this in components, I would say, and we can still use the x and y direction as we're looking at it, this guy is obviously going to be -5, 0, and this one is going to be 0, 20. I don't have to do that step, but it's something that you might have gotten used to in the last day when we were doing these problems. So the other thing I can do is I can just look at this and realize, wow, this is a 90-degree angle here, so this is going to be pretty easy to find the magnitude of the resultant velocity. I'm just going to use Pythagorean's theorem, right? So 5 miles per hour squared plus 20 miles per hour squared. And that magnitude, then you can go ahead and put that into your calculator, is going to turn out to be 20.6 miles per hour. Make sure you're checking me and doing the math with me, okay? You can always pause this and check your math, okay? And then I have to find this angle to get the direction, right? And I'm going to do that using my inverse tangent. And I'm going to say, well, that must be the inverse tangent of 5 miles per hour over 20 miles per hour. And when I go ahead and plug that into my calculator, I find that that's going to be 14 degrees. So the final answer, the resultant velocity with an angle, is going to be 20.6 miles per hour at an angle of 14 degrees. Now we have to figure out the direction. So I measured this, right? I measured this angle from this direction, which I know is north, and I have to go this way, so I have to go west to get to the vector. So I'm going to say that that angle is 14 degrees west of north. Okay, one more problem. Example 3. And let's say now that the velocity of the boat, right, just the engine providing the velocity, is going to be still this 20 miles per hour. But it's going to be at an angle of 30 degrees north of east, and the velocity of the water is still going to be due west, 5 miles per hour due west, so just like we had before. Okay, so let's take a look and see what we've got here. We've got to find our do our drawing here. So, and it doesn't have to be to scale, but you want to be close. So I'm going to go ahead, 20 miles per hour at 30 degrees north of east. That's kind of, we can call that, okay. So that's the velocity of the boat. And then the velocity of the water due west at 5 miles per hour, maybe something that looks like that. There is the velocity of the water. So then, if I want to go ahead and draw my resultant, I can see my resultant is going to look something like this. Okay, so that is going to help me out with my math a little bit. All right, so let's take a look here. We got to follow more of our process here. So I drew it out. The next step is to calculate the components. I already know the components for the velocity of the water. That one's pretty easy, right? It's all going to be in what we've been calling the x direction. So that's still that -5, 0. The velocity of the boat, I've got to do a little bit of trig work. So I'm going to go ahead and I'm going to draw another vector over here just to help me out. And I'm going to label that my 20 miles per hour. And I'm going to say, well, this is the velocity of the boat in the x direction. This is the velocity of the boat in the y direction. And I know this angle right here is 30 degrees. So I can use my trig and I can say, all right, I want to find the velocity of the boat in the x direction. So I'm going to use my cosine of 30 degrees is the velocity of the boat in the x direction over 20. And then the sine of 30 degrees is going to be the velocity of the boat in the y direction divided by that 20 miles per hour. So go ahead and pause the video right now and calculate what you get for the velocity of the boat in the x direction and the velocity of the boat in the y direction. All right, if you did that, you should have found that the velocity of the boat in the x direction is 17.3 miles per hour, and the velocity of the boat in the y direction is 10 miles per hour. So we could write that as a component if we wanted to. We could write 17.3, 10, and I'm just going to put the miles per hour up here, and I'm going to do that up here as well. Okay. So I went ahead and found the components for each, for the boat and for the water. So now we can go ahead and we can add those components. So the resultant velocity then is going to be, when I look at that, 17, let's see, that's going to be 12.3 miles per hour in the x direction and 10 miles per hour in the y direction. I can switch that over now to magnitude direction form because I can find the magnitude of the resultant vector just using Pythagorean's theorem, 12.3 miles per hour squared plus 100 miles per hour squared. Okay. And when I do that math, I should come up with 15.9 miles per hour. And then I can go ahead and I can look at the angle. Now the angle, to find that, I usually do like to draw the resultant vector just so that I have some idea of what the direction is going to look like. So when I see 12.3 miles per hour in the x and 10 miles per hour in the y, I know it's going to be a little bigger in the x than the y, so I draw something like that. And I say, okay, this was my 12.3, this was my 10, this is the angle I want to find. So theta is going to be the inverse tangent of 10 over 12.3. The units are going to cancel there. And I'm going to end up with, you should check this in your calculator, 39.1 degrees. So the final resultant of the relative velocity of this boat is going to be 15.9 miles per hour at 39.1 degrees north of east. All right, that's the last example that we've got for you. Go ahead and check Schoology, and there will be some practice problems for you to do. Thanks, guys.